Welcome back to this NPTEL online certification course in molecular rearrangement and reactive intermediates. In the last couple of classes I was talking about organoboron chemistry. So I started about the different reaction of organoboron compounds. I talk about hydroboration reactions, and then you have seen about the hydroboration oxidation, and then you have seen different type of chemistry, asymmetric hydroboration, and then selective hydroboration. In the today's class, and then also I think one of the important thing I have covered, if you must go back and go through that lecture, which is the reducing agent, like boron based reducing agent, like sodium borohydride, zinc borohydride. So these are all already discussed. In the today's class, my plan is to come back and talk about another very important chemistry is the allyl boron chemistry, and then talk about Sujui coupling and some other important reaction using organoboron reagents. So let us start with the allyl boron chemistry. So first I will talk about the allyl boron reagents, and then I will I think I will talk about the Sujui coupling, as I mentioned Chandlam coupling, then the boron-Wittig reactions, and then some of the conversion of organoboron compounds to other functional groups. So let us start with the allyl boron chemistry. So if I talk about the allyl boron chemistry, before that you have to understand the hydroboration. So you have already seen that if you have a single double bond, then after the hydroboration you can introduce the boron there, and then you can able to do the oxidation using H2O to NaOH, and then go to the corresponding alcohol. But now if you have a scenario like a cyclohexadiene, you have a 2 olefin here. Now if one of the double bond going to convert to the organoboron compounds, and then you can able to oxidize to the corresponding alcohol, you end up getting to the allylic alcohol. But the important thing to understand that when you are doing the hydroboration in this compound where you are going to convert to the corresponding alcohol, what is happening here? You can see you have a double bond here and you have done a hydroboration here, correct? Once you have done a hydroboration here, you have 2 different double bonds here. Now if you are doing a selectively one of this hydroboration, okay, then what is going to happen, you can end up introducing a boron here. So that can, if the boron is adding in this position, then what is going to happen, it can end up giving you a species where you have a boron here. Of course this this will be a trialkyl, as you can see there will be another cyclo. Okay, so you can add up thinking about that you are making this compound. Okay. After the hydroboration, because here you have a H, here you have a boron, and then you will be ending up making this compound, correct. Now if you think about, this is a functional group where you have a allyl group here and you have a boron here. So this is called a allyl boron compound. Okay, so it is actually forming a allyl boron compound as a intermediate at after the hydroboration, and then once you oxidize using H2O to NaOH, it is giving to the corresponding allylic alcohol. Now we can make so there are different type of allyl boron compounds. So let me try to write in about them. If you know about allyl bromide, correct. Now we are talking about allyl boron. So here you have a boron. Now it could be a different type of protecting group. You could have just OMe whole twice, dimethoxy, or it could be a pinnacle boron. That means you have a pinnacle as a protecting group. So you can see these are the compound called allyl boron compounds. You can see these are esters of boronic ester. Okay. Now you have another class of compounds where you can have a methyl group here. So instead of finishing here in the terminal position, if you have then these are called crotyl boron compounds. Okay. So now you can see that you are going to come to in a minute that once you have this substitution like here methyl or any other group here, that can also allow you to generate another extra stereocenter here. Okay. Now before I go to the reaction, I am going to talk about some of the synthesis. How do you make them? Suppose you have this diene here. Now what is going to happen, this if you see here one is here is this, if you try to compare these two one, then here this is a disubstituted one, here this is a monosubstituted one. So after the hydroboration using palladium catalyst, using catechol boron you can able to do hydroboration selectively here, and then the there will be isomerization as well, you will be end up making this compound. Okay. So, again you can see if you think about this particular type of allyl boron reagent, you can see. So, this will be, if you give them name as 1 2, then it will be a 2 methyl butynyl boron compounds. Okay. Again if you have this type of Grignard reagent, that could be this one, or if you start from allyl bromide and put some magnesium here, that can also generate you allyl Grignard. All these reagents, once you treat with this Cl B Ne2 that can generate these compounds where it will be eliminating Cl, generating Ba Ne2. Now if you put a protecting group like a pinnacle, that can remove this the dimethylamine and able to make this corresponding crotyl boronic esters. Okay. There are several other methods also developed. You can see using a very strong base, using N-butyl lithium and potassium terbutoxide, you can able to take this allylic proton, you can abstract this allylic proton here, and you can generate this allylic anion which can react with you have this triisopropoxide boron compound which can remove one of this isopropoxide group, and then what is going to happen once you treat with the H3O plus there, it can convert to the boronic acid. Now you can use a chiral diol. Okay. So, you can see here this will be a the isopropyl group here. So, it is a diisopropyl tartarate, you can use this one to do a protection. So, now you are generating a crotyl boron compound. So, this will be a E crotyl boron compound where you have a chiral diol here. You can also able to make the corresponding Z1 here, where you can start with the corresponding Z olefin of this so you have this olefin you started from which is Z. Now you treat with the again N-butyl lithium potassium terbutoxide, this stronger base can abstract this allylic proton, and then this this negative charge can again you are generating this anionic species which can react with this triisopropoxide boron compound, and then you treat with H3O plus, and again you do a protection of this boronic acid to get to the boronic ester. Now you are generating a chiral Z crotyl boronic esters. Okay. There is other methods, you can use a very important reaction here called the Mattison homologation. What is happening here? If you start from this this alpha dichloroboronic esters react with methyl lithium, then what is going to happen, the methyl lithium react with this boron to make B minus, and now there will be a 1,2 migration going to happen to get rid of this corresponding Cl species to generate this corresponding alpha chloro. And now as you have this chiral center here, I am going to come back to talk about this reaction, about this Mattison homologation reaction, how this chirality is getting controlled. I am going to talk about all of this, but once you get to this alpha chloro species, now once you have this vinyl lithium, if you can take this vinyl lithium and add here, you can now understand the vinyl lithium which is very similarly going to add here. Okay. And then it is going to transfer there will be 1,2 shift going to happen, because now it will be B minus, it will go for a 1,2 shift to get rid of chlorine to form this corresponding. So, you will have a 2 methyl again a crotyl species, but you have a 2 methyl here. Okay. So, now we have learned about different type of allyl and crotyl boron compounds. Now what are the different reactions we can use them. One of the reaction is you can take the allyl boron compound, you can take a aldehyde, it can react them to form this corresponding you can make this corresponding product here. Now the question comes how you are able to control this stereochemistry here, because you can see we are getting a anti-product here measure. Once we start from this E crotyl boron compounds, we get the anti as a measure, and once we start from the Z crotyl boron compounds, we got syn product as a major product. Okay. Now we are trying to understand how this type of allyl boron compound is reacting. So one of the important reactive parameter about the this type of allyl boron species is that once you take this boronic ester or the methoxy boron compound, as soon as you put a lone a Lewis base can give a lone pair of electron or give some electron density, or if you can have a base which can give electron density here, suppose you can I can consider as a B which can give a electron density here making a minus. Once you make this minus, this become a labile, so it can now react with a electrophile. So, that is how the allyl group can be transferred. So, here what is happening, your oxygen will have the lone pair which can be given to the corresponding the boronic ester. So, once this lone pair is given to the boronic ester through this 6 member transient state, it is going to give it to the corresponding product. Now, if you look into the 6 member transient state, one of the important thing, once you are trying to draw it, you have to understand, this is a E geometry. So, your methyl and this will be trans, which is you can see which is drawn here, and then this oxygen going to coordinate with the boron. This is a very important, because that is how the boron is getting activated for this allylation to be take place. And once it is happening, this bond is, so there is a formation of a double bond here, okay, because, and then you can see this bond is getting broken. So, this bond is going to form, and again this carbon oxygen double bond is getting broken. So, that is how you are end up generating this compound here. Finally, this oxygen boron bond is going to get cleaved, and that is going to form the corresponding product here. And you can see here, if you see your methyl and your oxygen is actually in the anti, okay. So, that is how it is forming this product. But once you start from Z, then you can see in the corresponding transient state we have to draw the methyl down, because the methyl will be in the axial position, because that can able to, now you can that can allow you to draw the corresponding transient state, because now this is a Z conformation here, and again you have this the carbonyl group here where the oxygen is coordinating with the boron. So, again this very similar thing going to happen, there will be new bond going to form, this bond going to break and going to form this product. Now, if you see here, your methyl is also down and your oxygen is this bond with the oxygen, and between this bond is also down after the cleaving of the boronic ester. You can get to the corresponding product, and this methyl and the oxygen will be in the same side. So, going to the corresponding syn product. Again, there are several other reactions of this allyl boron compound. It can react with a imine, and you will find very similar reactivity, where your nitrogen, at the time your nitrogen will have a lone pair that can give it to the boron, and very similarly this allyl group will be transferred to the corresponding imine to generate the corresponding amines. This type of reaction could be intramolecular, correct. This reaction with this the aldehyde and this allyl boron species. So, you have allyl boron species, reactive species, you have aldehyde. So, again once this oxygen going to, so once they are going to coordinate, they are going to react and going to form the corresponding product. Now, if you look into the product, you can clearly understand how this is forming. You must have a aldehyde here, and that is how this is getting attacked, and you can clearly understand this methyl group will be in the equatorial position, not in the axial position, because that will be generating the steric. So, that will be higher energy transient state. So, the reaction will follow the lower energy transient state to giving this product as a major product, and this will be your minor product. Again, if you come to this example here, if you see the changes happen here, previously this methyl group is in the next carbon of this double bond. Now, you moved one more carbon far. If you do that, still the reaction will be similar. This allyl boron species is going to react with your aldehyde, and in the transient state also you can see this methyl is going to be in the equatorial position, not in the axial position, because if in the axial position this will go through a higher energy transient state, going to give you the, so that will be the only 3%. Your major product will form where the methyl will be in the equatorial position. And now, if you use this reaction with a aldehyde, because now you have this chiral entity here, what is the point of putting this chiral group here? Because once you have this chiral group here, this can control the enantioselectivity selectivity of this new stereo center. Okay. So, now using this you can able to achieve up to 87% of enantioselectivity selectivity once you react this allyl boron species with the aldehyde. So, that is all about this allyl boron compounds. Again, if someone wants to know about more about allyl boron compound, there are some references given, you can go through them. I am moving to the Suzuki Miura cross coupling reaction. So, this is a very important cross coupling reaction. It actually changed the way we think about how to make the biaryl systems. So, this reaction was discovered in 1980s by Professor Akira Suzuki. So, he was awarded in Nobel Prize in Chemistry in 2010 for this great discovery. So, if you look into the reaction, this is a reaction of a aryl boronic acid. So, if you think at the beginning, you can say these are Ar, and you can see these are aryl bromide. Let us think about that way, or it could be a vinyl. So, aryl or vinyl. Okay, so those boronic acid or the organoboron compound, it is not always has to be a boronic acid, it could be a boronic ester also, and if you use a aryl bromide or different type of oxidating addition partner, in presence of palladium catalyst, heat and solvent and base, it can able to form the corresponding biaryl if both of them are aryl. If it is a vinyl, then it can make a substituted vinyl compounds. Okay. So, let us try to understand the different component of this reaction. One thing is nucleophile. So, there is a nucleophilic coupling partner and there is a electrophilic coupling partner. The nucleophilic coupling partner is your organoboron compound. It could be a boronate or a boronic acid, boronic ester or a boronate salt. In case of electrophile, as I said, it could be a aryl bromide. So, you have a aryl group, now it could be a bromo, iodo, chloro, it could be OTS, it could be O triplet. So, there are a lot of other groups could be which can participate in oxidative addition in the presence of palladium catalyst. And then of course, you need a palladium 0 catalyst of course, and then the ligand which can stabilize this palladium catalyst. Then base has a very important role, I am going to show you in the mechanism. So, usually the carbonate, phosphate or different alkoxide, the cesium fluoride or could be organic base used for this reaction. Of course, various different solvents are known, but usually you will see the dioxane, THF, DMF and toluenes are the very common solvent for this coupling, and you will always find there will be small amount of water usually needed for this reaction. Okay, you can add some water, and I am going to explain you why you have to add water for some of the cases. And then if you talk about the boronic component, just now I said you can use the boronic ester, the boronic acid. The thing is there are different type of the protecting group for the boron. It could be simple boronic acid, could be a boronic esters, or could be the salt. This is a the trifluoroboron salt, or could be a midaboron compound. If you think about this midaboron compound, one of the important thing is this nitrogen is giving electron density. So, this can stabilize this boronic ester much more compared to boronic acid. So, why this type of midaboronic ester protecting groups was developed? Because lot of the times if you have a heteroatom, like if you have a pyridine or if you have indole or if you have a different type of heterocyclic boronic acid, those are not stable. In the cross coupling reaction, they can decompose. So, stop the decomposition, the different protecting group was developed, and mida protecting group is one of the best of them. Because what is going to happen if you use this type of protecting group and a base, the mida protection can be slowly deported and form the boronic acid in the reaction, but the process will be slower. So, throughout your reaction you do not have a higher concentration of boronic acid. So, that is why the amount of boronic acid which is going to form is going to participate in the cross coupling to get to the corresponding product. So, now we will try to understand the mechanism of this reaction. Of course, as I mentioned, there are you need this palladium 0 catalyst. Of course, the palladium 0 can be formed in the different ways. If you go through your organometallic chemistry book, I think you will be able to find them. Now, once you have a palladium 0, it can participate in the reaction called oxidative addition, because here the oxidation state of palladium is becoming 2 from palladium 0. Okay, so, there is a addition and there is a oxidation, together we can tell them oxidative addition. So, palladium is becoming here, after the oxidative addition this aryl group is here, the bromo is here. Now, you have to go for a ligand exchange. What is going to happen? The bromo will be exchanged if you have this base, and then still keeping the palladium 2, and then the most important step going to happen called transmetallation. So, what is happening in the transmetallation step if you are using a boronic acid? If you are using boronic acid, lot of the times people use some water and some base like a potassium hydroxide. What is going to happen? That can generate this the OH minus can attack on the boron, can make this boronate species. So, you are generating this boron 8 species. So, once you generate them, now this R group are eligible for, because once you generate the boron species, the bond between this aryl group and the boron become weaker. So, now this aryl group can participate in a transmetallation reaction to get to this sort of intermediate. From there, after reductive elimination, you will be able to get to the corresponding biaryl. I hope you understand this, the mechanism of the Suzuki coupling. Now, the question comes, for a long time there was a question that is it this reaction only work with aryl boron compounds, or the reaction also going to work with alkyl boron compounds. Of course, it was later on developed that yes, the alkyl boron compound also can take part, So, alkyl 9 BBN compounds can be used. So, that can also synthesize from the hydroboration from the olefin using the 9 BBNH. So, that compound can react with a aryl halide or with a vinyl bromide or vinyl halides in presence of palladium catalyst, but there is an important you can see in this palladium catalyst you have to use a bidentate ligands. So, this bidentate ligand has a very important role in this reaction, because in this when you use a alkyl boron compounds for this cross coupling, the major problem was not this step, not the oxidative addition, because oxidative addition is still fine because you are using the aryl iodide or vinyl iodide or vinyl bromides, and then the problem, I think the transmetallation is still okay, but the problem was after this step the reductive elimination. After that the beta hydride elimination is a very common problem, and that is how you are not able to get to this corresponding the desired product, but instead of that you can end up forming corresponding styrene. So, to stop that, this type of bidentate ligand plays an important role to stop the beta hydride elimination to get to the corresponding product. As you can see, the competition experiments also explain that the order of the reaction, the iodo reacting the oxidative addition going to be faster compared to bromo, triplet, and of course compared to chloro, and that also depends on the bond dissociation energy of these bonds. Then again the bidentate ligands keep a cis complex, okay. So, that make a huge factor facilitating the reactive elimination and preventing the beta hydride elimination. So, that means after this step the bidentate ligands which play very important role to make sure that make a cis complex here with the palladium, correct. Once you have a bidentate ligand you are forming this cis complex, correct. So, once you have this cis complex formation happen, that can allow you, once you have this cis complex happen, so that can facilitate the corresponding reductive elimination once after the transmetallation step instead of the beta hydride elimination. You can see there are several different type of bidentate ligand was developed. You can see different class of ligands here. There are also NHC based ligands are developed, also they are sterically hindered. So, the palladium cannot take part in all these different type of side reaction which can also stabilize the palladium catalyst. Also there are monodentate ligand which was developed by the Buchwald group. These are also very useful ligand for the palladium catalysis. These are very reactive catalysis, and then also you have seen some ligands where you are using a bulky phosphorine. It could be a phosphorus, also this tarbutyl. Okay, so this type of different ligand also used for this cross coupling reaction. Okay. Now I am going to show you some of the application of this Suzuki-Miura cross coupling reaction. This is done in a industry for synthesis of different type of marketed drugs and a bioactive compound. You can see this reaction was done in 278 kilograms. Just look into this number. And if you see lot of this blockbuster drug synthesis, you will find the Suzuki coupling is used. You can see here using this palladium catalyst, and you can able to couple these two, where you have this aryl bromide and you have this organoboron compounds which is in this heterocyclic ring, can able to get to this corresponding product, corresponding biaryl product. Okay. There is another application here, the Suzuki coupling also used for the citronellyl derivative synthesis. Okay. For a you can see here also which is a natural product which is highly active against the leukemia. So, for synthesis of very important for a very important compound, we also use a Suzuki coupling here, because once you have synthesized these vinyl boron compounds starting from this corresponding aldehyde, now you can have this vinyl bromide, it can take part in the Suzuki coupling to get to this corresponding product. So, the other important reaction, so I already talk about Suzuki coupling. The other important reaction using a transition metal catalyst and organoboron reagent is a Chandlam coupling. So, this is a very important reaction, because you can see a lot of the marketed drugs you will find have amine functional group. Okay. So, this reaction can allow you to take a amine, if you take a secondary amine here, okay, and if you react with a organoboron compound, a boronic acid, you will be able to end up making to the corresponding. So, here you can introduce, you can make a aniline derivatives. Okay. Or if you start with a a phenol, instead of this amine, if you start with a phenol or alcohol, you can also able to get to this corresponding product here. So, this boronic acid, this aryl group will be transferred from the boron to this corresponding alcohol or corresponding amine. So, you can see here this is the you have a alcohol or amine to form the corresponding secondary amine or secondary aryl ether. So, you can also use the primary amine and alcohol as well. So, what is happening here, if you start with this phenol, let's think about if you started with phenol and a aryl boronic acid, what is this reaction. So, still if you find in the literature there are a lot of publication coming on the channel M coupling. So, if you use a copper acetate so pyridine is acting as a ligand here with the copper, and then it is going to form this species here. You can see this two ligand. So, first is the complex formation with the copper. Now, the important thing is transmetallation with the aryl boronic acid. So, that is actually bringing you to in this species here, this copper 2 species. Now, there is two possibility, it can go for a reactive elimination forming a copper 0, get to the corresponding product, or it can oxidize to copper 3, from there it can go for a reactive elimination to generate a copper 1 species, and it can go back to the catalytic cycle again. Again this the chain line coupling again used for the synthesis of biologically important compounds, biologically active compounds. Here you have this the boronic acid, and you can see you have this pyrrole. So, you can understand this can allow the cross coupling between this pyrrole NH and the boronic acid using copper acetate, very simple reagent, and pyridine. In the DCM in 3 days in the room temperature you can able to get to this product which can convert to these bioactive compounds. So, the other reactions is and the very important reaction using this organoboron compound and transition metal. So, now I think we talk about the palladium which is the Sujui coupling, the copper I talk about the channelam coupling. Now, I come to another important transition metal called rhodium. So, if you use the phenyl boronic acid in presence of this rhodium catalyst using a phosphine ligand, you can end up doing a 1,4 addition of this aryl group here. So, you have learned about this 1,4 addition chemistry, correct. I am sure you guys have gone through, I think I have already gone through organocopper chemistry, the Gilman reagent. You have seen that Me2Culi, I think you have seen that you can able to put this methyl group here, correct. And then if you remember, I also talk about that you can also make this center chiral if you use a chiral ligands at the time, okay. And so, now what I am talking here so there was a problem in that reaction, it will be difficult for you to introduce a aryl group here. So, but in this method we can use a aryl boronic acid, so you can see this is a very complementary method here, you are using aryl boronic acid here, and now this can allow you to introduce the aryl group 1,4 addition product. Okay. So, now the question comes, as you are generating a stereo center here with rhodium catalyst, if you use a chiral ligand which can bind to the rhodium catalyst, then you can able to control the stereochemistry of this to get to a particular enantiomers. So, here you can see by using this rhodium catalyst, so in place of the rhodium catalyst and the boronic acid makes an important role, using a 2.5 equivalent of boronic acid you can able to get to 93% yield and 97% of EE. Okay. So, here you can see the BiNAV was used as a catalyst with the rhodium. So, you can see this so rhodium actually forms some sort of bidentate, because you have the phosphorus here in the BiNAV which can form a bidentate complex with the rhodium. Okay. So, I am not drawing the entire BiNAV here, but here you can have the other ligand where here you have ACAC, all these other ligand can be bound here, which can allow the substrate to come in and participate in the reaction. You can see different type of substrates can take part, and they are giving very good yield and very good EE in every single cases. Okay. So, now what we are going to see, we are going to try to understand the mechanism of this reaction, how this reaction mechanism is going on. So, in place of the rhodium ACAX C2H4 and if once you add a BiNAV, first forms a complex with the BiNAV. As I said, the BiNAV, the two of this phosphine can chelate with this rhodium. But now there is important thing, once you have use a water in the reaction, that can also form this rhodium hydroxo species here, or if it can start the reaction from this species. I think this will be, so from the kinetics data where the Hayase group have published, they have seen this is a much more reactive species compared to this one. So, this can react fast with the boronic acid. Okay. Once you have this species, it can react fast with the boronic acid. So, first thing is there is a transmetallation happening. to generate this aryl rhodium species. So, this is a aryl rhodium species is generating. Okay. So, once this process is generating, then the next thing is there will be this aryl rhodium species now going to interact with this olefin here, okay, of this alpha beta unsaturated carbon compound, and there will be a insertion. So, this aryl group will be inserted here, and then the rhodium will be inserted here, but that will go for a O allyl rhodium. So, there is a oxo allyl rhodium species going to generate here, and then once there is a water that can get the compound get back to the the hydroxyl species of the rhodium, and you can get to the corresponding desired product. So, the important the role of water is, so that is why in this reaction high acid coupling you always find some equivalent of water was used that can help you first to form this the active catalyst, which is much more reactive compared to this one, and also helping you in the final step from this species to get to the corresponding product, and getting back to this corresponding the rhodium, the hydroxyl species. Okay. And as you can see, once you have this chiral ligand, chiral binary ligand that can control, so the chirality actually build up in this particular step. So, based on the chirality on the ligand that can transfer, that can allow you to add this aryl in the particular phase of this double bond, okay, to get to the corresponding chiral product. So, we have talked about lot about the transition metal catalyst organoboron reaction. Now, I am going to talk about some of the transition metal free reaction. So, one of the important reaction I am going to talk about today. So, this reaction is the called a boron Wittig reaction. So, we all know about the Wittig reaction. I think if you remember, in this reaction you can generate this phosphorus elite, correct. So, and then it can react with this corresponding aldehyde. If you have this R here and R dash CHO, then you can able to form this corresponding olefin, correct. So, here we are talking about a boron based ylides. So, how we are forming this boron based ylide, because once you have this geminal dibutene compound, that means your carbon has 2 boronic esters. So, if you have that scenario that you have a 2 bpene or any other protecting group on the same carbon, and this carbon has some other functional group, let us take R and this H, then this proton can be deprotonated very easily using lithium TMP, which is a very strong base, can able to allow you deprotonation to generate this species called okay. So, you generate this carbon species on the boron. So, you can think about this species as a very similar to this Wittig ylide of the phosphorus. This could be a very similar to a boron forming a ylide, because this negative charge can be donated to the boron, and you can think about a boron based ylide. So, this can react with a carbonyl group here, and after the reaction what is going to happen, this O minus going to form a bond with the boron, form this 4 member species. Then there is a boron oxygen bond formation happening here, and cleavage of this carbon boron bond to form this double bond to form the vinyl boron compounds after the elimination of this boron and oxygen. So, you started with the 2 different boron compound, using a base you can make the vinyl boron compound stereoselectively. So, the reaction originated in 1975 by Madison group. Here if you react this compound with methyl lithium, then that can cleave this bond to generate a carbon ion here. So, this is again generating a boron ylide, which can react with a carbonyl compound to form these vinyl boron compounds. Once you treat with H2O to NOH, this boronic ester can generate a OH, which can convert to the corresponding aldehyde. Okay. So, now after that this chemistry become very popular. The Shibata group applied this chemistry using acetophenone and other ketones. So, what he has done, he is allowed this synthesis of tetrasubstituted vinyl boron compounds. Okay. So, very important that this reaction comes with very high stereoselectivity. Okay. Then Morken group, they have 2 different publications on this topic, and they also solve several problems the reaction with the aldehyde. When you are trying to make a tri-substituted compounds, there are some problem with the stereoselectivity that can be solved by adding some extra base as additives. Our group also recently published very important discovery on this area, where we have shown that you can take isatine here and once in these cases what is going to have, you have two different carbonyl group here. One is next to the nitrogen, this could be this is the more reactive one. So, here you can react with this corresponding the boron ylite, and then that can able to form this vinyl boron compound. So, now you can see you are making some of these vinyl oxindole pieces, because these vinyl oxindole pieces are difficult to make using other methods. As you can see these compounds are present in a biological active compounds and in the natural products. So, you can able to make this using the boronotic reaction. We can also, we have shown that in not only using just like a alkyl aryl ketone, you can put a trimethyl silyl group here in the carbonyl group. These are called acylsilan. If you use that, then the important thing is now you have two different functionalizable group in this tetrasubstituted boron compound. So, what is the importance of boron compounds in this? Because once you introduce a boron compounds and a silicon, you can functionalize them using a Sujui coupling or other cross coupling reaction. We have recently shown another important application of this chemistry to one-pot conversion of phenol to carbonyl compound. So, it was a very difficult transformation to achieve without transition metal. What we have shown that you can use a phenyl iodoacetate that can oxidize this corresponding compound, this corresponding phenol to the corresponding queen ketal, and now once you use this boronotic reaction, this corresponding lithium can add here to this carbonyl, because this you can consider like a carbonyl group here, very similar to the boronotic reaction. You will form the vinyl boron compounds. Now, once you oxidize using H2O to NaOH, what is going to happen? This boron will be converted to the OH. Now, after the rearomatization, it will form the corresponding carbonyl compound. So, you can see in the one pot we have done all these transformations to get to this corresponding product. So, these are the references, and I hope you have learned about some of this allyl boron chemistry, Sujui coupling, the Hayashi coupling, the Chandlam coupling and the boronotic reaction. Thank you so much.